Here's a few example of acetals. I know we already did acetals in chapter 16, so here's a couple that you can practice. Looking at this first molecule, the acetal carbon, the carbon that used to be a carbonyl, is this carbon right here. That's the only carbon in this molecule that has two single bonds to two different oxygens. Everything else is an ether. This carbon is kind of like an ether over here. So that one carbon has two single bonds to two different oxygens. These bonds are going to be cut, these single bonds, and they're going to be replaced with a double bond to an oxygen. So let's go ahead and make a little line that we're going to cut that one and we're going to cut that one. So what do we get when we cut that one? When we cut those, I mean. We would get this. So this acetal carbon, the one marked in green, has a hydrogen attached to it. Only 3 bonds are showing. So this is an aldehyde. If you would like to draw the hydrogen there, you can. So we have an aldehyde. And then the other piece that we get is this, and these are the 2 alcohols that added to that aldehyde in order to make that full acetal. So this is a full acetal because both of these oxygens have R groups attached. Neither one of them is an OH group. This one over here is also a full acetal. That carbon over there is the carbon that has 2 single bonds to 2 different oxygens. Those are the bonds that are going to get cut and replaced with the double bond. So let's get that one. Again, that carbon has a hydrogen on it, so it is an aldehyde. You can draw the hydrogen if you like. So we have that. And then the 2 alcohol pieces, the 2 other pieces are these. They came from alcohols. So ethanol and this aldehyde going in the forward direction. So this is the carbon that is going to change to be the acetal carbon. Instead of that, we are going to have 2 single bonds to oxygen. We have this alcohol over here, but we also have this one over here, and this is a pretty good distance away from this carbon to make a ring. So that's probably one of the alcohols that's going to react. Let me go ahead and number these carbons. I'll number the oxygen as well. So we can make a 5-membered ring here. So here's 5, here's that oxygen over here. 5, here's 1, here's 2, here's 3. So let's go ahead and complete that ring. 4 and 5. And then this other alcohol can add in and make the full acetal. So first this will cyclize and you'll have an H here, but then if you keep cooking it in propanol, you will get the propyl group onto that oxygen. There. Let's try this other one over here. Looking at that carbon, that is the acetal. Hopefully you can find that. And we will disconnect these to get back the carbonyl that it used to be. Maybe we'll number these carbons as well. So we'll have this one be carbon number 1, the acetal carbon, then 2, 3, 4, and then if you want to have 5 be the oxygen, just so you could keep track of what it's going to look like once it's open. So we're definitely going to have some methanol here. That's going to come off. And then we're going to have a carbonyl here, that as being carbon 1, carbon 2, carbon 3, then there's going to be carbon 4. 5 is not going to be a carbon, 5 is an oxygen. Carbon 3 has an alcohol group on it. Carbon, well, it's not carbon 5. Atom 5 is an alcohol group. And then, yeah, that would be an aldehyde because the acetal carbon has a hydrogen attached. So you can draw that if you want. Okay, I think this is where we actually left off in the chapter. We were doing one more protecting group sequence over here. So this, we have a carboxylic acid and an alcohol, and we want to do something with the alcohol, but the thing we are doing might interfere with the carboxylic acid. So what we're going to do first is treat it with ethanol in acid. That does not do anything to an alcohol, but it does help to form an ester. So the alcohol would still be present, and we would have the ester here from the carboxylic acid. The side product would be water, but we don't really need to worry about that. 1, 2, 3, 4, 5. Yeah, we might get some 5-membered ring, but if we treat it with enough ethanol for long enough, hopefully we can get this to form. And then we have thionyl chloride that will make a chloride out of an alcohol. All right, sorry, my oxygen is a little skinny there. And then we can treat that alkyl halide with a nucleophile like cyanide ion, so that can displace the alkyl halide. And then there are a few things we can do with the nitrile. One of the things that we can do is hydrolyze it if we're in acid. Acid and water is also a way to hydrolyze the ester. So that's why we have 2 boxes here. The nitrile will get hydrolyzed. We'll have the carboxylic acid there if we heat it for long enough. So the carboxylic acid, 2, 3, 4. And then we have this also as the carboxylic acid. There we go. And then when it hydrolyzes that ester, it will release some ethanol as well. What would happen without the ester? Both carboxylic acids and alcohols can form chlorides, acid chlorides or alkyl halides with thionyl chloride. So one of them would form first. Let's say that the acid chloride forms first. It doesn't particularly matter which one forms first. I think this one will be slightly more reactive, but then this is very activated, and so we could have this alcohol cyclize around and attack. And alcohols and acid chlorides make esters, so that would make the cyclic ester. So we would have this cyclic ester. Even if we are saying that the chloride formed there first, we could still have this cyclize that way, giving us the same cyclic ester. So whichever one makes a chloride first, that becomes a leaving group, and then the other oxygen that's left can be the nucleophile, especially since it's a very convenient 5-membered ring that's formed. 5-membered rings form pretty easily and pretty quickly, so that's probably what would happen if we didn't protect the acid as the ester. Chapter 16, section 11 in your textbook, they had this unusual reaction that you could form a thioacetal. So instead of an acetal with oxygens, it's the sulfur variation. So this one has 3 carbons. If these were the 2 alcohols, these would be oxygens here, but they're sulfurs. And this is a little bit, if you have the one with sulfurs, it's a little bit unusual because you can hydrogenate it completely off and just make the alkane. I mean, this particular alkane is not very valuable. This would be a lot of trouble just to make cyclopentane, but if you had a molecule where you wanted to get rid of a ketone completely, this is an option for that. So this next section is the Baeyer-Villiger oxidation. We were able to get to this a little bit in class, but we'll just go over this pretty quickly here as well. If you have an aldehyde, this peroxy acid functional group with 2 oxygens, it will convert an aldehyde into a carboxylic acid. It can also convert a ketone into an ester. So this happens in base. The first thing that happens is that you have attack by an oxygen nucleophile to make something that looks like it's on the way to forming a hemiacetal, like we looked at before. But instead of getting a hydrogen and forming the hemiacetal, what we have is that this does a little bit of a shift, almost like the hydride shift, the 1,2 hydride shift that we had earlier, or the 1,2 methyl shift. So this moves over to be attached to this oxygen, and then that releases a regular acid rather than a peroxy acid. We have that shown over here as well. So we have the migration of one of the groups that was on the ketone. One of these R groups is going to migrate over to be on the oxygen now. If both of the R groups are the same, it doesn't really matter which one migrates. If you have a difference in the R groups. The most likely one that will migrate is an H, so that's why if you have an aldehyde, it's going to make the carboxylic acid, not the ester on the other side. Then the next most likely is tertiary group, and then secondary and phenyl are about equivalent, and then primary, and the least likely to migrate is the methyl group over here. So this methyl group over here is least likely to migrate. We're going to have this group migrate instead. So that's the side that gets the oxygen inserted. Here we have the hydrogen is going to be most likely to migrate because we're going to make the carboxylic acid instead of the aldehyde. The rest stays the same. This one we have this is going to be the one that moves. We'll insert an oxygen over there. So it's a 6-membered ring. We're going to try to make a 7-membered ring. The bottom's going to look a little bit like a stop sign here. And then the top is going to stay looking like the hexagon. Let's make sure we didn't change the skeleton too much. 1, 2, 3, 4, 5. And the 6th one has a methyl group on it. 1, 2, 3, 4, 5, and the 6th one has a methyl group on it. Comparing a primary carbon with a phenyl group, the phenyl group is more likely to migrate, so we're going to put the oxygen on that side. Keep the benzene ring intact. Those do not fall apart very easily. And we have that ester. So for the Wittig reaction, we're not worried about the mechanism, just the pattern that we see here. This is called a phosphonium ylide. There's a phosphorus double bonded to carbon over here, and there's an oxygen double bonded to carbon over here. So these groups are both going to go away, and then the 2 carbons are going to instead double bond to each other. And then the phosphorus ends up double bonded to the oxygen. But the main organic product that we're concerned about is this. So when you're thinking retrosynthetically, it's better to have a less hindered group on the phosphorus. This has to be made by an SN2 reaction. So having this bulkier group on the phosphorus is going to be more difficult to make. So if you're trying to retrosynthetically say, oh, I'm going to make this by a Wittig, you could make this side the phosphorus and this the oxygen, or this the phosphorus and this the oxygen. It's better to make the smaller, less hindered side the phosphorus. It's going to be hard to make this particular phosphorus compound here. So that's just one example of what you need to think about when you are thinking about how do I make a certain product, what would I start with. So that's the retrosynthetic thinking. We've been sort of touching on it here and there. They do have a little bit more in this chapter. They keep spending a little bit of time every chapter on giving you tips how to think of things retrosynthetically. Okay, so there's a few sections in this chapter also talking about direct versus conjugate addition. And this is something that we have to think about when we have an alkene right next to a carbonyl. So alkene over here, which is conjugated to this C double bond O over here. So we have a bunch of sp2 hybridized atoms all in a row. So we have some delocalization of these pi systems. And we can call this alpha beta unsaturation. So the alpha carbon is the carbon right next to a carbonyl. There's 2 alpha carbons here next to this carbonyl because we have a ketone. But this side over here has alpha beta unsaturation. If we delocalize this system, or we can think about this carbon as being electrophilic because there's a small amount of contribution where this carbon is positive and this oxygen is negative if we pull the electrons all the way onto the oxygen. That's not a major contributor, but there is some contribution which makes this carbon readily attacked, which is what we've been doing to these carbonyls for a number of chapters now. This cation you'll probably recognize is sort of an allylic looking cation, so this can also go here which would give you a positive charge over on this carbon as well. So this is also a resonance contributor. So we have some electrophilic nature over here to this carbon, and we have some electrophilic nature over here on this carbon. So both of these carbons are electrophilic. Either one of them can be attacked by a nucleophile. It depends. The conditions can be pushed or modified to give you one type of addition versus another. So if you add here to the carbonyl carbon, it's direct addition. This is saying over here. So direct addition is adding directly to the carbonyl. If you're adding to the alkene that's conjugated to the carbonyl, so if you're adding over here, then that one is called conjugate addition. So here we have some considerations to think about, trying to let you know when the conjugate addition would happen versus the direct addition. So if you're trying to get a carbon nucleophile to add, you can make a choice between a Gilman organocuprate reagent and a Grignard reagent. Grignards will tend to do direct addition, and organocuprates will tend to do conjugate addition. If you have some other weak nucleophiles, those will also tend to do conjugate addition. Most of the time you will get direct addition for hydrides or other carbanions if you don't weaken it, like making it an organocuprate or making an enamine when we learn about aldol reactions. The carbonyl itself does play a role. If the carbonyl is less reactive, if it's an alpha beta unsaturated ketone, especially if it's hindered, or if it's an ester or an amide, those are less reactive than aldehydes and acid chlorides. So those could be more likely to undergo conjugate addition. If it's very reactive, like an aldehyde or an acid chloride, it's more likely to undergo direct addition. So there's an example in your textbook of a hydride adding to a ketone. So since that's less reactive, that's favoring conjugate addition. But hydride is a more reactive nucleophile, so that's favoring direct addition. So you have some conditions that favor direct addition, some that favor conjugate addition, and you end up getting a mix of both of them. So this is the direct addition product. This is probably what you would have guessed. If this carbon reacts with hydride, it makes the anion here, and then you quench the reaction with ethanol. You can give that a proton, and you can get this over here. So this is the direct addition product. The conjugate addition product is the one where the hydride adds to the beta carbon rather than the carbonyl carbon. Then that pushes these up here, and that pushes these up here, which results in this structure over here. And then when you quench this, instead of this oxygen getting the hydrogen from the ethanol, instead of the enol, remember the ketone is favored. So these electrons, instead of grabbing a proton, will just come back and reform that CO double bond, and then these would get pushed out to grab the proton from ethanol. Let me draw that. Here we'll just draw the proton to show that that's getting a proton, and that leads you to this product. So the conjugate product, it looks like the alkene reacted, which might be confusing for you because we were learning that alkenes do not react with sodium borohydride. The alkene is not actually reacting with the sodium borohydride. It's just the alpha beta unsaturated ketone is doing a conjugate addition. But again, this is a mix of those two products because we get some direct and some conjugate addition for that particular reaction. I think these ones down below might be a little bit more in favor of one or the other product. Let's see if we can try those. So we have to do both, be able to predict whether it's going to do a direct addition or a conjugate addition and also being able to draw the product, the correct product, after we've made that decision. So here we have a hydride addition, which tends to do a direct addition. And instead of the ketone that we just did, we have an aldehyde, which is more reactive and tends to do a direct addition. So for both of those reasons, we're going to assume that this is mostly going to be a direct addition. And so that would be the probably normal product you expect for a sodium borohydride addition or a sodium borohydride reduction of an aldehyde. So we have that product. So here we have an acid chloride, which is very reactive, and so that's going to be more of a direct addition. So we have an alcohol reacting with an acid chloride, and that's going to do the normal ester formation that we would expect for that. So here, in contrast, we have something that's a lot less reactive than a chloride. We have an amide. So we're going to get a conjugate addition for this one. And that means this nucleophile is going to add to the beta carbon instead of the carbonyl carbon. And then when that carbonyl reforms, our product would look like this. So here we have the oxygen adding here, and in this one we have the oxygen adding here to this beta carbon. Remember, the copper reagents are more likely to do a conjugate addition as well. I'm going to draw the product over here. So instead of adding to that carbonyl carbon is going to stay there, and we're going to be adding to the beta carbon. So we have these two carbons added over here instead of over here. For a Grignard, we are more likely to get a direct addition. And so that ethyl group is going to add to the carbonyl carbon instead. So the alkene is going to stay there, and the two new carbons are going to be attached to the carbonyl carbon instead. Your textbook does have an example where there's a ketone, an alpha beta unsaturated ketone that is attached to a benzene ring, and they say that it's more hindered. The example in your textbook actually also has a larger Grignard, so theirs probably would do more conjugate addition, but just a little example of things to look for if you have a conjugate addition of a Grignard. So because it's hindered, you might be getting some conjugate addition product from this one. You probably would still get some direct addition because Grignards do like to do direct additions, but because it's a less reactive carbonyl, it's a ketone, it's also hindered, we might get some. So the two carbons adding to the beta carbon over here. Here was the beta carbon. Here's the beta carbon over here. So we would have two more carbons on that ketone here. All right, so I think that's the end of the note packet for chapter 16.